This program helps you to revise circuits and energy flow, magnetic fields, force and speed, force and rotation, hearing, and the solar system. First up, circuits and energy flow. Here's what you need to know.
Current is the flow of electrical energy around a circuit. Symbols are used to represent the different components. Like a cell, several cells together make a battery. A switch, a light bulb, and an ammeter. You need to know how simple circuits work and how the number and type of components can change the size of the current.
Watch this. The electrical wiring for a motorbike headlamp is hidden. Laying the circuit out on the floor makes it easier to see. It's made up of a battery, a switch, a wire going to the headlamp, and a wire from the headlamp back to the battery. Inside the lamp is a bulb. When the switch is turned on, the circuit is complete. An electric current flows and the light bulb works. But you can't see electricity, so what's actually happening? Electricity is a flow of negative charge around a circuit. The cell or battery pushes the charge through the circuit and provides the energy it carries. Imagine the charges are carrying bags of energy. As they pass through the light bulb, this energy is changed to light and heat. But the charges don't stop moving. They carry on round the circuit, picking up more energy in the battery. Electricity doesn't get used up. The charges don't change as they go through the bulb. It's the amount of energy they carry which changes. The size of an electric current depends on the rate of flow in the circuit. An ammeter measures current in units called amps. A current of 1 amp means that 6 million negative charges are passing through the circuit every second. Reading off the bottom scale on the ammeter, the current is 2 amps. So what will the current be here? No matter where you put the ammeter in a simple circuit like this, the current will always be the same. When the switch is turned off, the current can't flow because the charges can't move across a gap. When you add more bulbs next to each other, it's called a series circuit. So what happens to the brightness when there's 2 bulbs in series compared to 1? 2 bulbs in a series circuit are dimmer than 1 bulb on its own. The ammeter reading for this circuit shows that the current is now smaller. The flow of charge is less. Less energy per second is reaching the bulbs. Also, the charges now have to share their energy between the 2 bulbs, so neither is as bright as one on its own. What would happen to the size of the current in this circuit if more cells were added? Test yourself. This circuit is used to light a model house. The 4 bulbs in the circuit are the same. Which of these statements is true? A. The bulbs at the bottom are brighter. B. The bulbs at the top are brighter. C. Each bulb is a different brightness. D. Each bulb is the same brightness. This next section revises magnetic fields. Here's what you need to know.
All magnets are surrounded by a magnetic field. Place a magnetic material in this field and it experiences a force. Magnets also have poles, a north pole and a south pole. Poles that are different attract each other, and poles that are the same repel.
Watch this. The invisible force of a magnet acts over quite a distance. These tiny round magnets are all holding each other together. Their force of attraction is very strong. So, how can magnets pick up objects from a distance? The answer is that all magnets are surrounded by an invisible magnetic force field. This liquid-filled chamber contains iron filings. Place a magnet in the middle and you can start to see where the field exists. The iron filings are held in place by the magnetic field. Any magnetic object within this invisible field will be affected by the magnet. A computer scanning system shows the magnetic force field even better. As the scanner passes over the surface of this bar magnet, the computer plots a map of its force field. The strength of the field isn't the same all over, which is why you see a pattern of colour. Scan a ring magnet and the magnetic field is different. Different shaped magnets have different shaped magnetic fields. Back to the bar magnet, and another image makes the field strength even more obvious. The bigger the peak or trough, the stronger the magnetic field. For a bar magnet, the size of the field at both ends is equal but opposite and bigger than anywhere else. These are known as the poles. There's a north-seeking pole and a south-seeking pole. They're called this because when you suspend a bar magnet in mid-air, the red north-seeking pole will always point north. The blue south-seeking pole points south. Bring another magnet close to it and sometimes the poles repel. Other times the poles attract. These magnets are repelling each other. One pushes the other away. The rule to remember is that two north or two south poles always repel, but opposite poles always attract. So what's keeping these ring magnets in mid-air? Test yourself. The diagram shows a wooden truck near a wall. There's a strong magnet fixed to the wall and a strong magnet fixed to the front of the wooden truck. James holds the wooden truck so that it doesn't move. Then he lets go of the wooden truck. In which direction will it move? This next section revises force and speed. Here's what you need to know.
To understand how the speed of an object changes or stays the same, you need to know about forces.
With this toy car, the force of gravity is pulling down. The table is pushing up. These opposing forces are equal. So are any sideways forces.
When opposing forces are balanced, the car speed remains the same. In this case, it remains still. When opposing forces are unbalanced, its speed changes.
Watch this. Top cyclists can reach a speed of 15 meters per second, but during a race their speed will vary. To understand how something gets faster or slower, you need to know about forces. It's forces that change the speed. What are the forces acting on a bike and its rider? To move forwards, the rider needs to apply a forward force. She pushes hard on the pedals. This forward force changes the speed of the bike. It gets faster. But the bike doesn't keep on speeding up. Even though the cyclist keeps pedalling, her speed remains the same at 10 meters per second. That's because, as well as the force pushing the bike forwards, there are opposing forces trying to push it back. So what are these opposing forces? There's friction between moving parts on the bike, and the cyclist is pushing against the air. When forces are balanced, speed remains constant. What does our cyclist have to do to go faster? What has to happen to the forces? As she pedals faster, the forward force increases. The forward force and the opposing forces are no longer balanced, so the speed of the bike changes. It rises to 15 meters per second. But again, she doesn't just keep getting faster. That's because there's a small increase in friction in the bicycle parts and a big increase in the air resistance pushing backwards. The faster the bike goes, the greater the opposing forces. Eventually, the forces are balanced again and the cyclist reaches a new constant speed. To get faster, she's got to keep making the forward force bigger than the backward force. Racing bikes like these don't have any brakes. Instead, the cyclist simply stops pressing down on the pedals. The forward force is now much smaller. The forces are unbalanced again, so the speed of the bike changes. This time, it gradually slows down. What's happening to the forces as she stops? Test yourself. Megan's dog is pulling on its lead. Megan has to pull to keep the dog still. Suddenly, the lead breaks at the dog's collar. What will happen to the movement of the lead and why? This next section revises force and rotation. Here's what you need to know.
When a force acts on something which has a pivot, it creates a turning effect. Levers have pivots. A pivot is a fixed point about which the lever moves. On a wheelbarrow, the pivot is at the centre of the wheel. Remember, the object being moved by the lever is called the load. The force applied is called the effort. The size of the turning effect depends on the size of the effort force and its distance from the pivot.
Watch this. The Moscow State Circus acrobats are world famous for their daring acrobatic skills. In their speciality act, one acrobat stands at one end of a springboard, while another prepares to drop from a height onto the opposite end. When the jumper hits the board, the harnessed acrobat is catapulted into the air. It relies entirely on a simple lever. The pivot is at the centre of the springboard, the point about which the lever turns. The load is the acrobat standing on the board. The effort force is provided by the acrobat jumping from a height. As the effort force pushes down on one end, the load is lifted at the opposite end. As with all levers, there's a turning effect. The effort force on the left-hand side of the springboard produces an anti-clockwise turning motion. So what happens when the effort force is increased from one jumper to two? Increasing the effort force increases the height gained by the acrobat. The turning effect of the lever has increased. You can calculate this turning effect by multiplying the size of the force by its distance from the pivot. The turning effect is equal to the force times this distance. Let's go back to just one acrobat. He has a mass of 100 kilograms, which means he lands with a force of 1,000 newtons at a distance of 1 metre from the pivot. The turning effect is 1,000 newtons times 1 metre, which is 1,000 newton meters. So what about two acrobats? Their combined mass means they land with a force of 1,500 newtons. This time, the turning effect is 1,500 newtons times 1 metre, which is 1,500 newton meters. If the pivot was moved further to the right, the force would be acting from a greater distance. How would this change the size of the turning effect? A spanner is a very common lever. It's a handy tool when you want to change a wheel. But with a short spanner, the job is impossible. Take a piece of scaffolding pole and make it into a longer spanner. Apply the force again, and this time the nut begins to turn. The same force is acting from a greater distance, increasing the turning effect. In science, the turning effect of a force about a pivot is known as a moment. Test yourself. Gareth is trying to release a nut with a spanner. The diagram shows the size of the force he is exerting and where this force acts on the handle. The spanner applies a moment or turning effect to the nut. Calculate the size of this moment or turning effect. This next section revises hearing. Here's what you need to know.
Sound is made when something vibrates. Vibrations create sound waves in the air which are detected by your ears. You need to know how vibrations travel through the ear and are converted to electrical signals which pass to the brain.
Watch this. How do you hear the sound of a drum? A sound wave is like the wave you can make on a slinky spring. You put energy into it by pushing one end. This compresses the spring. The compression travels along, carrying the energy with it. Each coil is pushed forward and then springs back to its starting position. What carries the wave when you hear a sound? Air is made up of tiny particles, which are far too small to see. When a drum skin is struck, it bends inwards and then outwards, compressing the air in front of it. It's the compression that moves through the air, leaving the particles back where they started. The drum vibrates many times every second, so a sound wave is made up of lots of compressions. But what happens when sound reaches your ear? The shape of your outer ear helps it to catch sound waves and funnel the sound into your ear. The next thing the sound waves hit is the eardrum, which vibrates just like an ordinary drum. Then the vibration continues through 3 tiny bones. They amplify the sound and transmit it even further into the ear, to a curly region called the cochlea. The ear bones pass on the wave to a liquid inside the cochlea. The movement of the liquid is picked up by cells shaped like tiny hairs. They send electrical signals to the brain along a nerve. The ear converts sound waves into electrical signals which the brain can recognize. Sounds can be low-pitched or high-pitched, depending on the frequency of the vibrations. A high-pitched sound is a high-frequency sound. That means there are more vibrations every second. But how do you hear the difference between sounds of different pitch? When a low-frequency sound enters the ear, it's detected nearer the centre of the cochlea, and the brain recognises a low-pitched sound. When a high-frequency sound comes in, it gets detected in a different place, nearer the entrance to the cochlea. This makes a different electrical signal, and the brain recognises a high-pitched sound. Test yourself. The diagram shows part of an ear. Sound waves enter the ear and make the eardrum vibrate. The pitch of the sound is increased. What difference will this make to the way the eardrum vibrates? This next section revises the solar system. Here's what you need to know.
Our solar system is made up of the Sun and 9 planets. Moving outwards from the Sun: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune and Pluto. Let's make that a little bit easier to understand the order. My very excellent Martian just sat under 9 planets. As well as the order of the planets, you need to know how the Earth's movement gives us day and night time.
Watch this. The Earth is one of a family of 9 planets orbiting a star called the Sun. As the Earth moves around the Sun, it spins on its axis, which helps explain the difference between day and night. The Earth spins on its axis once every 24 hours. Imagine you're standing on the Earth and looking at the sky. During the day, you're facing the Sun. As the day progresses, it looks as though the Sun is moving, when in fact, it's perfectly still. At night, you're facing the stars. As the Earth spins round, you pass by the stars, which makes it look as though they're moving. The solar system is huge, almost too huge to imagine.
We're making a model of the solar system.
We've worked out on our scale that if the sun is this big,
the planets would look like this. Mercury,
Venus,
Earth, Mars,
Jupiter, Saturn, Uranus,
Neptune,
Pluto.
And on this scale, the distance between the sun and the furthest planet, Pluto, would be 3 kilometres.
And so we need a really big space, a really, really big space, and a little bit of help. Bye, Sam!
If the sun's the size of a large beach ball,
Mercury!
Mercury's a coriander seed.
Venus!
2 planets almost identical in size are Venus and Earth.
Earth!
They're both as big as a black currant.
Mars!
Mars is the size of a peppercorn. Jupiter, the biggest planet, is still only the size of an orange.
Saturn!
Saturn's the size of a lemon.
Uranus!
Uranus and Neptune are about the same size as each other. They're the size of a large grape.
Neptune! Pluto! That's me!
And Pluto is a tiny onion seed. On this scale, you can see how the 4 inner planets are quite close together. But after Mars, the distances between the planets get much bigger. Jupiter is 710 kilometers from the Sun. Saturn is 1,427 million kilometers from the Sun. Uranus is 2,871 million kilometers from the Sun. Neptune is 4,497 million kilometers away, and an amazing 5,914 million kilometers from the Sun is Pluto. The nearest star to our Sun is Proxima Centauri, which on this scale is somewhere in Australia. Test yourself. Mars is the 4th planet from the Sun. Name one planet which is closer than Mars to the Sun.